Hello judges, we're Iron Rain, Team 6832, and this is our Control Award video submission. Before we begin to look at any actual code, I'd like to start by giving y'all a quick robot overview. Meet Talbot. Talbot is our robot for this game season, and Talbot was designed to be both efficient and also incredibly unique. The main parts of Talbot, or the main two subsystems, are really the underarm, which includes the chariot and the actual underarm itself, and the main chassis along with the crane. Our general scoring pipeline is the underarm goes and picks up a cone controlled by driver 2. They meet together here in the middle for a handshake, and the main crane picks up and then scores the cone. Our robot contains a couple of sensors that make it much easier to code for and to drive. First off, we have our Logitech webcam that detects which zone we need to park in for Auton and provides just standard video feedback. We have a distance sensor here at the very end of the crane. We have another distance sensor in between the crane, or the main chassis and the underarm right here, which helps tell us how far the chariot is from the main chassis. We have an IMU on the main linear slide right over here, and then we have an IMU on both the control hub and the expansion hub, which are in the main chassis. That's the control hub. The expansion hub is on the underside of the robot, and both of those help us maintain our robot's heading. Up next, we have articulations. Articulations are a robot's way of combining a bunch of precise, minute actions to create larger sequential blocks of code that operate on the robot's main system, rippling to create larger, more detailed actions on each of our robot's subsystems. For example, our most complicated articulation is the transfer, which you can see here. Up next, we have inverse kinematics. Our robot's crane is driven almost entirely by an inverse kinematics model, which we derived using trig and visualization on Desmos to calculate angles on both the crane and the underarm. This enables us to automatically calculate the angles on our subsystems simultaneously to navigate the crane and the underarm to known points on the field. This makes driving and coding much easier because all the coder has to specify is an XYZ point on the field, and the crane automatically calculates the angles necessary to get the bulb gripper to that. Up next, we have our IMU-based anti-tipping code enabled by our PID loops. So we made custom PID loops for all of the joints that need regulation on our robot. Our robot comes equipped with two internal IMUs that enable us to find our heading on the field, which informs the navigation systems with the robot position and the turret angle. The robot has an additional IMU mounted on the bottom side of the crane, which monitors the angle of the crane system and prevents the robot from tipping catastrophically. When the crane IMU senses that it's tipping too far, it temporarily shuts down the robot to regain stability. Here you can see the crane extend, and the anti-tipping code using the PID loops kicks in to help reduce the oscillation. Up next, we have our simulator and our dashboard. Our personalized simulator and dashboard are tools that we built that allow us to remotely test autonomous code based upon physics concepts of torque versus force, and they use feedback from each of our PID loops to allow for an accurate simulation of the robot to test code, especially in autonomous. Up next, we have our AprilTag vision pipeline. We use an OpenCV pipeline to read April tags on the randomized cone for the autonomous section of the match. Using a webcam, we read what the randomized April tag is set on, which returns an int to us from 1 to 3, and our robot goes to the corresponding zone in the last 20 seconds of Auton to get the most points possible from parking. Up next, we have scoring patterns. In the robot's memory, we have a virtual map of the field, including positions of substations, cone stacks, and junctions, and this factors in the robot's current position. Using this map, we can algorithmically determine the most optimum sequence of junctions to score on, which allows the arm to approach a given junction autonomously and with a high degree of accuracy. This complements both our driver strategy and our code strategy greatly.